In this video, we are going to answer this question: how can photons have momentum although they do not have any mass? Although this question have been answered by numerous people, however, I am going to take a different approach to answer this question, and as a result, we are going to learn certain important aspects of physics, including Planck-Einstein relation, what is the quantum nature of photon, how Higgs mechanism work, and can we use the power of a photon's momentum to make a spaceship move. My name is Shaunak and you're watching this video on Physics for Students. I welcome you to my channel. Before we go ahead and start this video, I would like to draw an attention to our viewers that this is the first video on a fresh series of lectures which I am starting on special theory of relativity. First of all, let us look into what are the topics that we are going to cover. So first of all, we are going to understand what is the nature of a photon. Do photons have momentum, and what would be the mathematical way to derive and understand that? How Higgs mechanism work, and does Higgs mechanism gives mass to a photon? What is called a space-time interval? What is the derivation of the momentum of photon? What is the quantum nature of photon? And an important aspect which is called a solar sail, in which we are going to learn that how can we use the power of the momentum of a photon and use it in direct industry use. Before we go ahead and start with the topics, let us first understand how and where this concept of photon evolved, because I consider it is always very important to understand the basic nature and the brief history of the concept before we start and go ahead with the topic. So a photon is derived from this ancient Greek word phos or photos, which actually means light. It is an elementary particle that is a quantum of the electromagnetic field, including electromagnetic radiation such as light and radio waves, and the force carrier of electromagnetic force. So here phos and photons means light. So photons are massless, so they always move at the speed of a light in vacuum. The photons belong to the class of bosons. As with other elementary particles, photons are best explained by quantum mechanics and exhibit the wave-particle duality, their behavior, feature, properties of both waves and particles. So a photon is a massless boson and it carries a wave-particle duality, and in general in mathematical calculations the Greek word gamma is used in order to denote a photon. Now Arthur Compton used the term photon in 1928, referring to Gilbert Newton Levy, an American scientist who coined the term in a letter to Nature on the 18th of December 1926. In most theories up to the 18th century, light was pictured as being made up of particles. Since particle models cannot easily account for the radiation, diffraction, wave theories of light were proposed by René Descartes in 1637, Robert Hooke in 1665, and Christian Huygens in 1678. However, particle models remained dominant chiefly due to the influence of this person, Sir Isaac Newton. In the early 19th century, Thomas Young and Auguste Fresnel clearly demonstrated the interference and diffraction of light, and in 1850 wave models were generally accepted. James Clerk's Maxwell's 1865 prediction that light was an electromagnetic wave, which was confirmed experimentally in 1888 by Heinrich Hertz's detection of radio waves, seemed to be the final blow to particle models of light. As shown by Albert Einstein in 1905, some form of energy quantization must be assumed to account for the thermal equilibrium observed between matter and electromagnetic radiation. The Annus Mirabilis paper, which appeared around Friday the 13th of June 1905, forever changed our way in which we look into the nature of space and time. Here is the upper cover of Einstein's special theory of relativity. Annus Mirabilis, which comes from the Latin word mirabilis, which means miracle year, are the 4 papers that Albert Einstein published in Annalen der Physik, or the Annals of Physics, a scientific journal, in the year 1905. These 4 papers were major contributions to the foundations of modern physics. They revolutionized science understanding of the fundamental concepts of space, time, mass and energy. Because Einstein published these remarkable papers in a single year, 1905, that is why it is called Annus Mirabilis. The first paper, photoelectric effect, explained the photoelectric effect, which was the only specific discovery mentioned in the citation awarding Einstein the Nobel Prize in Physics. The second paper, Brownian motion, which led reluctant physicists to accept the existence of atoms. The third paper introduced Einstein's theory of special relativity. The fourth is a consequence of the theory of relativity developed by the principle of mass-energy equivalence expressed in the famous equation E equals to mc squared, and which led to the discovery of use of atomic energy. These 4 papers, together with quantum mechanics and Einstein's later theory, general theory of relativity, are the foundations of modern physics. So we know that photons are massless because they travel at the speed of light. A photon is a packet of light, well, actually a packet of electromagnetic radiation. You can have X-rays, gamma rays, ultraviolet rays, infrareds, microwaves, etc. Now, one can presumably slow down light in optically denser medium, right? But in reality, the light travels at c, that is the speed of light. The exception, the next step is that there is an invariant speed called the vacuum speed of light. This that happens to be the speed of light when it travels in vacuum. So it is called an invariant speed because all observers agree with that speed. Normally speed is relative to the observer, as we have noted. However, this is one exception. This exception has a consequence. Anything that travels in the invariant speed of light, which include photons, can never be at rest. So here on the third point I have mentioned, if you can't find a photon at rest, then since it has no rest mass, it has zero mass energy. That means it doesn't exist. So mass is associated with objects at rest. It is sometimes called rest mass. So it is because photons travel at the speed, special invariant speed, that they can never be at rest, and hence cannot have a rest mass. The trick was figuring out there actually was an invariant speed in the first place, but once we got there, the photon was forever doomed to be massless. Okay, now we come to the central part of the video where we would be talking about, does photon have any kind of a momentum? Now, you may have already are aware about that light consists of electromagnetic waves. The wave nature of light, however, is actually unable to explain some phenomena such as the photoelectric effect. Right, where a light beam can actually scatter off electrons and it knock it off from a piece of metal. Now, it was Einstein who won the Nobel Prize, first proposing that actually light consists of little finitely sized packets of energy, that is elementary particles. Here you can see that these energy packets hits the electrons and they transfer it into kinetic energy. So energy and mass are actually related to each other, and from there we come to the final point that mass is just another form of energy. So from Einstein's special relativity, we know that mass is just another form of energy, but in the case of a photon, since it is always moving at the speed of light, it cannot have any mass, which is a consequence of Einstein's relation. So without energy, how could it produce the photoelectric effect? So all of the energy of a photon is in the form of motion, which we are going to discover very soon. Okay, so we continue with this equation equal to mc squared, but the problem is that this is not the full equation. The original equation comes up to here. So what we see is e squared equal to, we are not going to look into this derivation, you can just understand this. Now this is actually the right kind of a, I would say, right kind of a equation. Now this is the mass, this p denotes the momentum, and this c denotes the speed of light. Now if we put, for example, numerically m equals to 0, considering mass to be 0, then we get e squared equals to this, which brings us to the equation E equals to P times C. So this equation E equals to P times C is actually energy, which is equal to the momentum multiplied by the speed of light. Now photons get their energy from momentum, and hence if we consider now P to be 0, now first we consider mass to be 0, now we are considering the momentum to be 0, then we get this kind of a equation, and removing the square roots, what we get is E equal to mc squared. So this E equal to mc squared comes into play when the particle is at rest, right? So we saw two parts. One is that when mass is 0, the entire energy of the photon is the speed of light multiplied by the momentum, and if we consider the momentum to be 0, we get E equals to mc squared. But remember, this happens when momentum is 0, means the particle is at rest. Okay, so we go ahead with this equation which we have got, right? And if we set m equals to 0 and p equals to 0, right? What we see is this, which further leads to this, and which further leads to this. So here what we get is that energy equals to 0. But an object with 0 energy and 0 mass is actually nothing at all. Therefore, if an object with no mass is to physically exist, it can obviously never be at rest. Such is the case of light, right? So an object with 0 energy and 0 mass has nothing at all. So if an object with no mass is to physically exist, then it can never be at rest. Its entire energy is coming from the energy of momentum. So the object travels at some speed v that is less than the universal speed limit c. So we can always choose the reference frame, which I was earlier referring, traveling along with the object, so that the object will be at rest in this reference frame. Therefore, an object that can never be at rest must always travel at the universal speed limit c, which is the speed of light, because this speed has the interesting property that once an object goes a speed c in one frame of reference, it goes in the same speed c in other frames of reference. So to summarize, all objects with no mass can never be at rest and must travel at its c, that is in all speeds of light. Now here is an important observation, that massless photons still appear to be affected by gravity. Now I'm not going to take ahead with this topic in this particular video, but I'm sure I'm going to make another video in which I'm going to explain how a massless photon, how it can be affected by gravity. Now here is a question, very important and fundamental. Is photon the only particle to be massless in our universe? The answer is no. We have something which is called as gauge bosons, which is one of the family, or for the timing you can just assume as one of the fundamental particles, which can be divided into three parts. First one is the photons, which are massless, and we are observing its properties. The second one is called a gluon. It is an elementary particle. It acts as the exchange particles or gauge boson for the strong force between quarks. It is something similar to the exchange of photons in the electromagnetic force between two charged particles. Gluons bind quarks together, forming hadrons such as protons and neutrons. So this is one particle which is also massless. The third one is a graviton. Now in theories of quantum gravity, the graviton is the hypothetical quantum of gravity, an elementary particle that mediates the force of gravitational interaction. There is no complete quantum field theory of gravitons due to an outstanding mathematical problem which is called renormalization in general relativity. In string theory, believed to be a consistent theory of quantum gravity, the graviton is a massless state of fundamental string which has not yet been detected. So apart from photons, these are the two fundamental particles, gluons, which acts as an exchange particles for the strong force between quarks, and gravitons, which is hypothetical quantum gravity which has not yet been detected. Now we all know that all these particles are massless. So this brings to a very important and fundamental question, because we know from Peter Higgs, who won the Nobel Prize, that Higgs boson or the Higgs field gives rise to mass. So if the Higgs boson gives mass to other particles, then how and why photons escape it and are massless? So in order to understand this fundamental question, we go ahead in the next part of our video, which is going to quickly explain you what is the Higgs mechanism. So to explain what is Higgs mechanism, I'm going to divide it into different parts. The first part, I will consider that all elementary particles are merely excited state or quanta of some field. I'm so sorry that I don't have a proper animation to show it, but just consider a field which is being excited. This includes Higgs boson, which is the quanta of the Higgs field. So quantization, if I talk what is actually quantization, then it is basically a field consisting of discrete energy parcels. So from continuous we are moving into something discrete. So a quantization is basically a field consisting of discrete particles. Here, just for your imagination, I've just drawn certain abrupt figures. So you can consider each of the blue box to be a state of energy in this, in between this, the black box or the black circles are, each of them are discrete energy parcels. Now this includes the Higgs boson, which is the quanta or quantization of the Higgs field, the photon, which is the quantization or the quanta of the electromagnetic field, the electron, which is the quanta of the electron field, and so on. So all fields actually exist at all points in time and space. This is the first part in explaining Higgs mechanism, that the elementary particles are merely excited states, and a Higgs boson, photon and electron are all quanta of different fields. Okay, we also know that fields may couple or interact with each other. And in this case, the fields are said to be interacting with each other. This is a simple example of what is gluon coupling. This is another example of fields coupling. And this is another example of mechanical, electrical, thermal fields which are coupling. So all in all, what we need to understand is that fields do interact with each other. Okay, fields may couple with other fields also. Now, here I would like to show you a small kind of an animation. Now, say consider A, B, C, D, E to be fields, right? I just wanted to consider this to be fields. Now, remember that we will soon explain, after a process which is called spontaneous symmetry breaking, the Higgs fields is separated into two parts. Now, here right on your screen, this is the Higgs field, and as you can see, these green lines are basically showing interaction of field A, B and D with the Higgs field, because I just told you that some part of the field do interact with the Higgs field, which gives rise to two parts. The first one remains what is called a vacuum expectation field, which we are going to explain what it is. And the second one is called the dynamic field of the Higgs boson. Okay, now let us consider this orange to be also fields, right? So the equations that describe the coupling of the Higgs field to other fields, they become themselves a part of the quantum field theory. So here, these blue lines, okay. So I just wanted to tell you that these are the interactions of the vacuum expectation value, which we will soon learn what it is. So the it is interacting with those fields F, which are marked in in orange. Now, in return, these fields also interact with each other. As you can see, the red, the black arrows, let me show you. These are also the fields which are interacting with each other, right? So the equations that describe the coupling of the Higgs field to other fields become equations that describe the other fields coupling. That is the second one, that is this black arrows, a coupling to themselves, which in quantum field theory is interpreted as giving mass to a field. The vacuum expectation value in the Higgs field is actually proportional to the mass of each field. So what is a vacuum? See, this actually goes over here and this actually gives mass. So let me repeat that the vacuum expectation value of the Higgs is therefore proportional to the mass of each field, and the equations that describe the second type of field coupling quadratically to themselves, which in quantum theory is interpreted as giving mass. So if you really want to see the animation once more, just to clear up, here is the first field interacting with each other, which are marked in blue, and these are the second field that in return which interacts with each other. So the equations that describe the coupling of the fields, Higgs fields to other fields, become the equations of the other fields coupling to themselves, which is interpreted in this dotted lines is that which gives mass. Okay, fairly clear enough. Now the vacuum expectation value of the Higgs field is just the value that we would expect. Okay, that is why we call it an expectation value. That we would expect it to have when it is in a vacuum state, which is in the lowest energy state, right? We know that vacuum is the lowest energy state. Now it turns out that it is a general law of nature that physics, a physical system always wants to be in the state of the lowest possible energy. The allowed values for the energy are determined by the system's potential energy function. So here you see the value that we would expect it to have when it is in vacuum, that is the lowest state, and it is physical system always wants to be in the state of lowest possible energy. So the thing is that values for the energy are determined by the system potential energy function, and the potential energy function looks something like this. This is a kind of a funny picture. It is called basically a Mexican hat potential. That means if you draw the graph, it would come like this. It is a three-dimensional graph. The two horizontal axes are the values of the field that it can take, and it corresponds to each specific value phi. It is a kind of a, you can say, geographic terrain where the values of the fields are the latitude and the longitude, and the value is at the potential. So here is a cartoon or a figure sitting right at the top, and it says, oh, it costs too much. I think I should go around there. So we have a large valley, try to imagine, with a small hill at the center on which the Higgs field is currently sitting in the image on the left hand side of your screen. However, the Higgs looks around and notices that there are lower energy states all around him at the bottom of the valley. It wants to roll down the hill into a state of lower energy. So we have a large valley with a small hill at the center on which the Higgs field is sitting, and it wants to come to the lower energy state. So here what happens. So you notice that when it is at the top of the hill, the system is completely symmetric. Why? Because you can rotate the potential on the vertical axis as much as you want, and it looks exactly the same. But after the Higgs field rolls down, here it rolls down, right? This one, I would say this, let's see the graph again. Yeah. So here is the rolling down with this red arrow. So when the Higgs roll down into the lower energy state, we say that it acquired what is called a vacuum expectation value, VEV. So here you see VEV on the left hand side of the screen. The first figure shows 0, but now it has come down and it has acquired a vacuum expectation value, right? Note that the vacuum expectation value is the value of the field. It is not the energy. So previously when it was on the top of the hill, the field's VEV was 0. This can be easily seen from the fact that it was the origin at the center of the horizontal plane, but the field equals 0. Now the field has a non-zero value and it has a lower energy than it had before. So pretty clear, the Mexican hat actually shows that the Higgs field was sitting right at the top, but as physical system always wants to come down, it rolls down to a lower energy state, and this is exactly what is called the spontaneous symmetry picking, and it has got some kind of a value. So we go ahead with this figure. Let it be on the right hand side of the screen. So the expression on the now this is actually the equation. Now let me explain with you what it is. So this phi would be the Higgs field, this psi would be the particle, and the psi with a bar is the anti-particle, and g is basically the coupling constant, right? So these are the different parts. Now why we are mentioning it is right over here what we see is we get a VEV equals to V. Why? Because we just want to give a VEV a value, and from here what we get is this. So the expression on the left is where the mass comes from. Okay, first let us combine this. Yeah, this is the V, right? This is the V. Now what we have done over here is thus we are combining the value with a phi, V and G together. So we get this part. Yeah. So the expression in here, this is the interaction term, right? This is the interaction term between the particle. As you can see, there is an anti-particle and there is no third field. So such an interaction is basically the mass term. So here is H, which is the new field. According to quantum field theory, as I told, it gives electron or positron a mass m. They did not have it before, right? There was no term before. So the value of the Higgs field, this H, is actually this part, and this is actually what we call, it is the Higgs boson, and this is how the Higgs field gives mass to the particles. We will further explain it right now over here, but this is overall how it mathematically looks like if we take the particles from the standard model and if we interpret. So we got a Higgs field, we got a particle and anti-particle. The right hand side is the interaction term. H is being the new field, and this actually gives what is called the Higgs boson. Okay, so we get of these particles. Now this part is basically what is called the where the mass comes from. These two are actually different numbers. So in order to get the number, what we do is that we equate the equation m equals to gv. Now m is just anything. I mean to say, you can do it of x, t, s, whatever. Because they are just numbers, we are just combining the g and v with m. Then we get this kind of an equation. This part, which is the red, it is this part. So you see that m equals to gv when once this gv is substituted over this value. So we get m equals to gv. Now you're substituting this. So we get this kind of an equation, right? So we take it forward, and this is basically the number. So this is the interaction term between the particle and the anti-particle. This actually gives the electron and positron, just to name that it has both mass m. So with the help of the Higgs fields VEV that I was talking about, the V that is the vacuum expectation value, we have managed to create a mass term out of nothing. So this is how the Higgs fields give speeds to the particles. That means the more they are interacting with the particular Higgs field, the particles will gain more and more mass. So it is simple that if I am traveling from a place to another place, and if there are more people around me, then I will interact and it will take more time for me. I gain the mass, and if I do not, and if I am empty, then I do not have any mass. So this is the most important part. What we have done is that we have equated the number g and v with m, because these are two numbers, and when we substituted this value that m equals to gv, so it becomes m psi bar with psi, and psi bar is the anti-particles and psi is the particle, and m is actually the number, and it shows that how we get a mass. Although this is not a very strict open kind of a definition, however, this is a kind of a nice analogy in order to know that how Higgs field produces mass. But we have not answered this question. How does photon escapes the Higgs field? Now here is the standard model. You can see the leptons, you can see the gauge bosons, and here we have got only 12 particles that gets a mass from Higgs mechanism. These are the 6 quarks, 3 leptons, 2 gauge bosons, and the Higgs particle boson itself. However, photons is left out. The reason that the photon is left out is this, that there is no exchange of particles between the photon and the Higgs field, and therefore they don't interact at all. So what we can tell is that the answer is quite straightforward. It is because the Higgs field does not interact with it. All massive fundamental particles acquire their mass from interaction with the Higgs field. In particle physics terms, we can tell that an interaction can be defined as an exchange of particles. Therefore, two particles with exchange gluons are said to be interacting strongly with each other, since the gluon is the gauge boson transmitting the nuclear force. In the same context, there is no exchange of particles between the photon and the Higgs field, and hence they do not interact, and because they don't interact with each other, they do not have any mass. So this answers the question that how photons escape the Higgs field, and because of the less amount of interaction, they do not have any mass. So what we can summarize is this: Higgs boson is a quantized excitation of the Higgs field, and so are the electron and photons. The Higgs boson gives mass as a part of the electroweak symmetry breaking, which we call as, we have seen what is called the spontaneous symmetry breaking. Higgs field acquires this non-zero value at the electroweak symmetry breaking of a value of around 100 giga-electron volt. The vacuum expectation value actually breaks the electroweak gauge symmetry. Breaking of this symmetry show the electroweak scale about 246 GeV, which leads to a broken weak symmetry, but the electromagnetic symmetry is left unbroken, and because electromagnetic symmetry is left unbroken, the only gauge boson remaining massless is the photon, which is related to the unbroken part of the electroweak group. So this summarizes and gives you the answer that why photons are massless and how the Higgs field acquires mass by symmetry breaking, spontaneous symmetry breaking, and what is the VeV, that is the vacuum value, and how we get that vacuum expectation value, and how we arrive to getting mass of all the fundamental particles. However, photon escapes it, and it retains its status of being massless. Okay, so we come to the derivation of the momentum of a photon, and we will go ahead with the mathematical details very simply, and we will learn certain other details. Now, based on the classical Newtonian mechanics, the formula of momentum equals to mass times velocity, then a photon would have any momentum as it has no mass. A photon cannot have a momentum without a mass, so Newtonian mechanics must suffer from some difficulty, because we will need something more fundamental, that is the theory of special relativity. So the goal is to find a definition. So here you see that mass momentum is something related to the mass. So we need to find out a definition for momentum expressed in terms of energy, which is not dependent on mass. That is actually not difficult to do, and we will soon see. But before that, we need to have an understanding of two important concepts of special relativity. The first one is called space-time interval. Now, because we call it as an interval, so we have already seen in numerous videos, if you're watching my general relativity videos, that space and time are intricately related to each other. Space is not space, time is not time. So a mathematical model that is combining 3 dimensions of space and 1 dimension of time together is called a space-time interval. We also have one concept which is called a proper time interval, and proper time is associated with trajectories, which is called a world line. However, we won't use the term world line for this part, but it would be proper time is the time elapsed that is measured by an actual clock traveling along the trajectory. So in physics, space-time we have seen is a mathematical model that combines it into kind of a 3 dimensions. Now here is something I would like to show you. This particular equation, this is the equation of space and time, space-time interval, where the left part is the time part and the dx, dy, dz would be the space part. We also can write it in a tensorial form or in a tensor format, which makes life easier. However, we are not going to deal with what is this tensor format, but we have clearly understood what is a space-time interval and how the equations look like. Okay, so here is something which we call it as in 3 dimensions. So here is one event A and B, and this is delta D, which is the distance, and in 3 dimensions the distance delta D can be written as this, which can be further written as delta S square equals to delta CT square. And here are the 2 events which is separated by delta X. I know I should have written delta X a little bit later, but anyway it doesn't matter. So as far as the concept is concerned, first event and the second event, observer is watching, and it is different. The difference is delta T. So what we do is that in 3 dimensions, the distance D, delta D between the parts, we use actually the Pythagoras' theorem, and we can write it as delta D square. And then in 3 dimensions, events will be coming up and computing into space-time interval. Now this observer measures 2 events which is being separated by delta T, which is the spatial distance, and delta X, into time, that is delta T, and the spatial distance delta X. Then the space-time interval delta S square would look like this, and in 3 dimension it would look like this. Now this one is when the events are considered as infinitesimal close to each other. We can use the differential term ds squared to be so. This part is actually the time part, and this part is actually the space part, which I was just explaining you that the space-time interval is divided into 2 parts. So one is divided into ds squared, this one is the time part, and this is the speed part. Just note that this c is the constant speed of light, which converts into time. Delta S square is the squared interval, is a measure of separation between events A and B that are time separated, and in addition space separated, because they are separated by 2 objects or because of single, and the separation interval is derived by spatial distance from A and B, which we have seen here. Now here is a small point of note which I would like to tell. You might find across in textbooks or in other resources, ds squared, the space-time interval, is sometimes written as this and sometimes written as this. As far as the convention of the signs are concerned, both of them are correct. Right? So both of them are correct. You don't need to worry that which one is right and which one is wrong. So both of them are correct. So we have understood till now what is a space-time interval. If there are 2 events which is separated by the distance d, how do we compute and how do we write in 3 dimension? However, there are 2 events, event 1, event 2, separated by delta x. So how do we write that? And in 3 dimension, how the space-time interval looks like, and what is the time part and what is the space part. Okay, so now what we do is that we know that proper time is this one. Okay, c squared equal to d tau squared. But what we are doing is that we are dividing both the sides, right, by d tau square, and what we get is this. Now if we use that space-time interval, we get this. I don't need to explain much, we are just substituting the values, right? So we get to this, and we further solve for dt by d tau, and we get this. And we are using square root values, and we get this. And using the square root further, we get into this. So I mean to say, you can just take a note of how we are solving things, because this is not much of a difficult mathematics, I believe. So yeah, so that is how it happens. So just note one thing over here, that we have just taken derivatives with respect to proper time. Right, so this is the derivative with respect to proper time. Okay, so now what we do is that we take forward this one, and just one note you have to understand, that what is this terms. Okay, we get further into this. This one, this red boxes. So what is the sum of the squares of these derivatives? These are simple velocities, right? So for example, dx by dt is just the x component and velocity. So together with these three terms, we simply get the total velocity, which is this one. Now this looks very similar. I'm sure that you are guessing what it is coming to. Then we get into this, and then we can write as this. This is actually the Lorentz factor. So I have just written, because Lorentz factor is sometimes also written as gamma dt by d tau. So what we have seen is that the square of these terms, these time derivatives, are simply velocities from further we have deduced, and we have got the Lorentz factor. Now let us look at the derivatives of the spatial components with respect to d tau. Here we will need another component, important concept of special relativity. So derivatives of the spatial component with respect to d tau. It is something which is called a force velocity. I'm sure that you are aware about force velocity. The idea of force velocity is not at all difficult. It is simply velocity with four space-time components t, x, y, and z, opposed to the normal space-time component x, y, and z. And force velocity is denoted by this one, u raised to the power superscript mu. So the normal velocity is defined as the derivative of the spatial components with respect to time. So we can call it is just the relativistic counterpart of the normal velocity. So this is till now which we have understood. We have got the Lorentz factor, and we are moving with the force velocity. Now in classical mechanics we know this, right, as the formula for momentum. And in relativistic, we also have got something like this. So you can just calculate that it is mass multiplied by force velocity. Since we need to analyze the spatial component of this, we are going to denote them by this one. This is the momentum, this is the mass, and this is the force velocity. So for the spatial dimension using I, we are using pi is equals to mu mui, and solving for mu I, you will see that we are getting into this. Now u here is simply the total force velocity of the space components, right? So ui equals to pim. U is basically the total force velocity. Here I have mentioned the total force velocity of the space components. For example, ux is equal to px by m, and uy is equal to py by m, so on. Now the derivatives of the space components with respect to the proper time would be this one, right? So we will carry on with this particular derivation, and we will soon see something interesting. Okay, so we already know this. Now here this red box is basically the square of four velocities, right? These are the square of four velocities. So now what we do is that dt by d tau square, we put it as a gamma, and when we substitute dt by d tau equals to gamma in c square gamma square, we get this, right? So it comes to so dt by d tau equals to gamma, so it is put up into c square term, and it results into c squared gamma square minus this term, right? So dt by d tau becomes gamma, and from there we get into gamma square. This is actually this one, which I call the derivatives of space components with respect to proper time. So here is something we need to come across, something very important, is that what is a relativistic total energy. We know that relativistic total energy is equal to E equals to gamma mc square. Now rather than considering a more fundamental quantum mechanical, this is the fundamental mechanical energy. So once we square both of these sides, we get E square equals to this one, and then we further get into this. So now we insert, okay, if you want to go back, you can do. We are carrying with this last equation, gamma square c squared equals to E square upon m squared c squared. Now we are inserting this equation into this. So gamma square c squared is now put into c squared y squared. So we are substituting this gamma square c squared, and what we get into this. You see, c squared gamma squared, once it is put into this one, so it becomes E squared upon m squared c squared, and it results into this. So we get this pi, and then forget I for the time being. What we are doing is that If we are considering p is the limit which is extending towards 0, then we get this one within the square root, we get e squared by c squared, and we remove the square root, we get e by c, and you see now we have got the momentum of a photon, p equals to e by c, which is actually the momentum of a photon. Now you might be wondering that we got the same value but just a few minutes earlier by just substituting m equals to 0 when mass is 0 and p equals to 0 when the momentum is 0, but we haven't considered the space-time interval, which is a key of special theory of relativity. So all these equations and derivations are just to make you understand that what is when we consider the space-time interval and how do we calculate the momentum of photon. So left hand side you can again go back and see how we have done that. It is a nice clear equation solving. We inserted the value into y squared c squared, and then we got c squared gamma squared in over here, and then we further substitute this value, we got e squared by m squared c squared, and we solved out for p. So this is value, put the value into c squared gamma squared, and then c squared gamma squared is put into p squared. Now the thing is that this leads to the conclusion that momentum of a photon is proportional to its energy. Now the next question that we comes across is that how do we calculate the energy of a photon if the energy is defined as equals to gamma c squared, which is the relativistic energy. How do we do that? So for that, what we have to now do is that we have to understand a little bit about the quantum nature of a photon. Now if we really wish to consider the energies and momenta of particles such as photons, we do have to take the quantum mechanics as well. So the first thing is to do is that let us forget the above the definition of E equals to gamma c squared. Now at the turn of the 20th century, this person which you are seeing on the screen, Max Planck, deduced maybe partly by accident that the nature of electromagnetic radiation was actually not continuous, right? But it has got certain discrete packets of energy, right? And Max Planck hypothesized that when the light was emitted, it is not continuous, but rather it contains certain quanta. This is a nice demonstration, and I would also like to show you this one. Potential energy of a person walking up a ramp increases uniformly. However, walking up the stairs or steps would take up in a quantized manner. So this is basically what Max Planck found out. And later, this great person, Albert Einstein, who won the Nobel Prize for the photoelectric effect, for showing that energy packets in fact are massless particles, which became to be known as photons. So the photoelectric effect shows that photons had to have energy that is proportional to the frequency of electromagnetic waves, and that is why this strikes off the electrons from a metal plate. Now, why I am showing you this? Because both of them are intricately related with each other. Together, the work of both Max Planck and Albert Einstein can be expressed into one methodical, I would say, equation, which is known as the Planck-Einstein relation, and which is this one, E equals to HF, right? So the Planck relation, also called as Planck's energy frequency relation or Planck formula, is a fundamental equation of quantum mechanics, which states that the energy of a photon, E is known as the energy, is proportional to the frequency times the Planck's constant. If you consider the value of Planck's constant, this is in terms of joules hertz. This is the frequency, and you will also see that it is sometimes written as E equals to h nu. The constant proportionality is h, or it is written as E equal to h bar omega, where h bar equals to h by 2 pi. It can also be written to this. So the relation accounts for the quantized nature of light and plays a key role in understanding phenomena such as the photoelectric effect and the blackbody radiation. which was later postulated by Planck. So now we need to understand that this one is the fundamental constant in quantum mechanics. It expresses the quantization of light and matter. Now, in the last years of the 19th century, Max Planck was actually investigating the problem of a black-body radiation some 40 years earlier proposed by Kirchhoff. Now, every physical body spontaneously and continuously emit electromagnetic radiation. There was no expression, I have written in third point, or explanation for the overall shape of the observed emission spectrum. At the time, Wien's law fit the data for short wavelengths and high temperatures but failed for long wavelengths. So, approaching this problem, Planck hypothesized that the equations of motion, light, describe a set of harmonic oscillators, one for each possible frequency. He examined the entropy of the oscillators, varied with the temperature of the body, and he tried to match Wien's law and was able to derive an approximate mathematical function. So he tried to match it with the Wien's law and deduce some kind of, and that is what we are doing. So Planck-Einstein relation is extremely important. Why it is important? Because since light is an electromagnetic wave, so it obeys the basic wave mechanics. So it has got a speed c, frequency f, and wavelength lambda, and which can be connected into this equation, c equals to lambda f. We can also note that speed of the light is c, lambda is the wavelength, f is the frequency, and solving for f we get this. And remember that the energy can also be expressed in terms of wavelength by inserting into the Planck's equation E equals to hf. If we put this value, f equals to c by lambda, we get E equals to h times c followed by the lambda. Now we are going to use the equation from the earlier, which stated that momentum of a photon is proportional to the energy, which is this one, P equals to E by C, and connecting both the relativistic and the quantum mechanical equations, what we get is this, right? So we get P equals to E by C, E because we know is hc by lambda, E equals to hc by lambda, it's upon C, then it comes to h by lambda. Now this one we have actually substituted. This is actually what is known as the de Broglie relation, which connects to the momentum to the wavelength for what is called is a matter wave. So the de Broglie equation is also written as lambda equals to h upon p, right? It is also written as h upon p, and this is actually what is called matter waves, and lambda is also known as the de Broglie wavelength. So what we see now from here is that lambda equals to h by p is this one, which can also be written as m0, which means the rest mass. This is the momentum. So finally we have arrived at a relation which gives us the momentum without the mass of the particle. So you see this equation, I'm so sorry. This is how it looks like. This is how it looks like. So this is again when we consider the quantum mechanical aspect, and when we equate the Planck-Einstein relation, we also get and arrive to the same conclusion where the photon have a momentum, although it doesn't carry any mass, and that is how this comes into play. Okay, so the final part of the video is now to help you and show you how can we make the momentum of a photon work. I mean to say, we have all seen photon, momentum, photoelectric effect. We have deduced certain equations, but ultimately, does it at all help to mankind? Does it have any industry experience? I would say implementation. We have something which is called a solar sail. Okay, so solar sails, let me explain to you, are the only method of spacecraft propulsion in which no fuel will be required. Obviously, I mean to say, when you're pushing the rocket, the propulsion technique right from the base won't help in solar sail, but once it is into the orbit. So until recently, spacecraft powered by solar sails were the stuff of science fiction. However, following the success of the Japanese spacecraft Icarus, which flew close to Venus in 2010, and in 2019, the crowd-funded lightsail 2 spacecraft, it is likely that spacecraft powered by solar sails play an increasing role in future space exploration. So light is made up of packets, as you can see, photons. While photons have no mass, they have momentum. Solar sails captures this momentum and push things forward. This is two nice photographs. The right one is that of Icaros, which is on its way in 2010, and this is how we make use of the momentum or the force, enormous force of photon, and how we can make things move forward. Okay, let us see quickly that how a solar sail works. Now we know that light consists of photons. Whenever photon hits the surface of a mirror, it is reflected back at the same angle. So here is when a photon hits the mirror, it strikes back at the in the mirror, and here is a demonstration. So here is the sun and here is the mirror, and I threw a light. The light is emitted from the sun and it is striking the mirror. So some of the photon's momentum is transferred to the mirror, pushing it in the direction, this, the red one, right? Pushing it in a direction which is right angles at the surface. And some part, the net effect of the vast numbers of photons in sunlight is to generate force or thrust, and some part of it is reflected. So this is the reflected path of the photon. These are the two angles, theta. Now, because the direction of the thrust, it has right angles to the mirror surface, it is possible to change it by orienting the mirror at different angles to the sun and make the spacecraft maneuver. So if again I tilt the mirror a little bit, here I strike and it goes around this way, and here is the angle and it reflects in this way. Again I put the mirror in this way, and here how it goes and hits the mirror, and this time it goes in this way and it reflects in this way. So the basic idea behind this solar sail is that by angling the mirror and calculating the angles how much we are, it is possible that we can push and thrust the sail of a spaceship on any kind of a stuff like that and maneuver it in different directions. So changing the orientation of the mirror actually helps us to maneuver this spacecraft. Now remember that in reality no mirror is 100% efficient. So reflecting all the sunlight that hits it, some light is obviously absorbed. The direction of the thrust caused by the photons, which are absorbed rather than reflected, is always where the light is coming, regardless of the orientation of the mirror. That means it will always like this, and when it hits over there, it will be like this. So that is what it is important. This is illustrated below. In addition, the maximum thrust caused by the absorbed light is only 50% of that which is caused by the reflected light. So the direction of the thrust caused by photons, which is absorbed rather than reflected, is always in the direction. So this is how it happens. So I mean to say that is basically the practical application of the momentum of a photon in order to maneuver and move a spacecraft. So that's all. We have come to the end of the video. So we have learned about the origin and the nature of a photon, what is called the momentum of a photon, how photons do not get mass, and what is the Higgs mechanism. We have also noticed what is Higgs mechanism. We have explained it. We have looked into the derivation of the photon of a momentum. We have also looked into the quantum nature of photon and what is solar sail, and using the momentum of a photon, how we can operate and maneuver a spacecraft. That's all. I think the video has given you a nice idea about how the photon gains a momentum without being a mass, and I tried to explain it a little bit detailed way. We have also learned Higgs mechanism. So do like, subscribe and click on the bell icon to get all the notification from Physics for Students. This is Shaunak signing off from today, and wish you a great and a happy weekend ahead, promising you to come back very soon with another interesting video on physics and mathematics. Till then, goodbye and stay safe and stay happy.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.